In this video, we'll look at mass to mole calculations. And again, I don't usually follow step 1, step 2, step 3. They're fine, but I'm not going to try to memorize that for a test or quiz. I want to know this method. Stoichiometry is all about ratios. So in order to get the ratio, I need the balanced equation. In number 1, I have, moles of carbon dioxide formed from the combustion of 25.8 grams of ethane. I don't care about that 25.8 grams. Right now, I just see the combustion of ethane, and I need to write the balanced equation. Ethane is a 2-carbon chain, single bonded carbons, and the carbons would be surrounded by hydrogen. Hydrogen, hydrogen, hydrogen. So my formula is C2H6. Combustion means that we are burning the organic in the presence of oxygen to produce carbon dioxide and water. I need to balance this. So I'm looking at 2 carbons. 3 times 2 is 6 hydrogen. And my oxygen. All right, 2 times 2 is 4. 4 and 3 is 7. But all I have here is O2. It's this little guy that's making it an odd number, so let's double it. Instead of 3, let's make it 6. Now we're going to have to go back and fix some things. 2 times 6 is 12 hydrogen. Now I need 4 carbon on both sides. 4. But then this would be 8 and 6. And I could get you 7 times 2, 14 oxygen. And now it's time for stoichiometry. In the problem, there'll be one numerical value, and that's where I want to start. I have 25.8 grams of ethane. Now, in the last couple of videos, our original number was given in moles. And so we could use the balanced equation right away to switch to moles of something different. Problem here is that my original number is in grams. Eventually, I want to know how many moles of carbon dioxide will be produced. So I want to switch from ethane to carbon dioxide. And I want to be able to use that 2 to 4 ratio. But that is not a ratio of grams. It's a ratio of particles or moles. So now if your original number is grams, we need to get it out of grams. And we need to turn it into moles. Oh, so again, the mole calculation, it never leaves you. It stalks you forever. The periodic table gives me molar masses. Anytime I see grams, I'm just going to add it using my periodic table. Maybe about 30.08. And the periodic table's mass is for 1 mole. The molar mass is the mass of 1 mole. All right, there. Welcome back, January. We could have done that in January. Now that I'm at moles, I can switch to whatever I want. I'm at moles of ethane. I want to cancel moles of ethane. We need moles of carbon dioxide. Enter in the ratio from the balanced equation. 4 to 2. I feel good when I cancel my units, and the only thing left is the unit that I want. How many moles of carbon dioxide will be formed? So there was just a little extra step here. If the original amount is given in grams, you have to switch it to moles first. Then you can use the ratio in the balanced equation to compare different substances. We can plug this in our calculator. We'll divide by anything on the bottom, multiply by anything on the top. It doesn't matter what order you plug it in your calculator. So I could go 25.8 divided by 30.08 times 4 divided by 2. is 1.72 moles of carbon dioxide. If the original number was in 3 sig figs, you can still leave 3 in your final answer. So you don't have to let the significant figure thing drive you too crazy. Done. If this method clicks for you, you're in a really good place. Stoichiometry is a method. It's nothing to memorize. In the same reaction as above, how many moles of oxygen would be needed to completely react with 25.8 grams of ethane? So if I have a certain amount of ethane, how much oxygen would I need to completely burn it all? And so, again, we cannot use grams. This 25.8 grams of ethane needs to be converted into moles, which we kind of already did, so we'll set it up exactly the same. Cancel grams, turn it into moles. What you want goes on the top. What you want to cancel goes on the bottom. This is so driven by units. I always put the units in first because then the numerical part should be easy. Whenever I see grams, I go to my periodic table. 30.08. The periodic table gives me the mass of 1 mole. The molar mass. Grams cancel. Now that I'm in moles, I can switch it to whatever I want. We'll cancel moles of ethane. We want moles of oxygen. Moles of oxygen on top. We plug in the ratio. 7:2. Fabulous. We can cancel moles of ethane. You are gone. And then that's it. That's the setup. 25.8 divided by 30.08 times 7 divided by 2 with 3 significant figures. I'm going to say 3.00 moles of oxygen. There it is. Eventually, when I get stoichiometry problems, we want to be at this point. We want to be to the point where we can convert between different substances in the balanced equation. We can compare amounts of reactants or products. The only way you can compare different substances is by using the mole ratio. So if you don't have moles first, then you'll need to change it to moles before you can use the ratio. So there's another one here. There's one about, oh gosh, like a lead problem with like a lead battery. It's pretty awesome. Pause it at this point. Give it a shot. Then bring it back. See how it goes for you. Let's see if you're getting these right. All right, here it is. We have a car battery producing electrical energy from a reaction between. Okay, so this reaction is a little crazy, but they tell you everything. The reaction is between lead metal, just Pb, solid lead 4 oxide, lead plus 4, oxygen minus 2, and sulfuric acid, or sometimes it's called battery acid. And we are given the formula H2SO4. The products in this reaction are solid lead 2 sulfate and water. So they tell you all the reactants and products, and we don't need phase symbols. We don't have to worry about no reactions. It works. If the battery loses 0.34 kilograms of lead in this reaction, how many moles of lead 2 sulfate will be produced? Now, by saying that the battery loses 0.34 kilograms of lead, it means that's the amount of lead that gets reacted. Now, eventually, we want to be able to use the periodic table to get that guy out of kilograms and into moles, so that I can use the ratio between lead and lead sulfate. So the only little trick here is that if they do give you kilograms, it's probably best to switch it to grams. 0.34 kilograms would be like 340 grams. Then since I'm given grams initially, we'll cancel grams of lead, switch it to moles. 1 mole of lead has a mass of about 207 grams on my periodic table. And then I can make the switch. We're going to cancel moles of lead and switch it over to whatever I'm looking for, which in this case is the lead sulfate. We'll take that 340 grams, divide by 207.2, and multiply by 2. With 3 sig figs, we're looking at about 3.28 moles of lead sulfate. Nice, huh? And again, like once you kind of get used to this setup, it's like you get in a rhythm. Now you could switch it to anything in that equation. We're starting with 340 grams of lead. We could switch it to whatever particle we wanted. In number 4, how many moles of sulfuric acid will be consumed if 0.34 kilograms of lead are used in this reaction? And so again, we'll use the 340 grams because the periodic table's masses are in grams, and I want to get this out of mass in grams and into moles. And then I can make a switch. Well, check this out. You can compare reactants. You can compare reactants to products. In either case, between lead and lead sulfate, or lead and sulfuric acid, it's a 1-to-2 ratio. These end up being the exact same number. Well, what do you know, huh? I would cancel moles of lead. Cancel moles. There we go. Switch it to moles of what I want. Sulfuric acid. Plug it in your calculator. They end up being the exact same thing in moles because it's the same ratio in the balanced equation. Okay, so now looking into the future. Here's what the next video will do. What if I wanted to measure these amounts in grams? What if they said how many grams of sulfuric acid, how many grams of lead sulfate? Well, it ends up being the same amount in moles, but these two would have very different masses. Their molar masses will be very different. That's what we'll do in the next video. We'll bring these back to grams, which is probably what we would use most often in the lab.